There's a profound difference between describing a phenomenon, as detailed as this description might be, and seeing the phenomenon. Those are completely different modes of understanding. That's one of the reasons why scientists make computer simulations. In this case, we use technology to drive and stimulate human interaction, engaging people to take part not as an audience, but as performers. We created a series of games and organized a workshop in order to try out with students things like the Ising model or the Monte Carlo algorithm.
The aim of this workshop was to approach physics, especially statistical physics, in a playful manner.
People can themselves play as human computers and interact themselves with concepts of computational science in a playful way.
We, for example, reproduced the so-called Ising model. The Ising model is also called the Drosophila of statistical mechanics. It's the basic model that describes phase transitions like freezing or melting. It even describes the making of gluons in the early universe. The particular thing about it is that it is a lattice model, which makes it very suitable for a workshop for the public, for example, because every participant can be a computing node and can make computations themselves. In our particular case, we wanted to emulate with the participants the computation of the freezing transition. What we had was a grid on the floor, and each participant stood on one grid point. All of the participants have little shields with colors on them that was signifying their current state. One of them was frozen and the other one was liquid. When the game starts, a participant is randomly selected, and this participant has to play rock, paper and scissors against the other neighbors. In order to change their state, namely from liquid to frozen, the participant has to win more than half of its neighbors. The mechanics of the game should mimic the algorithm that we use in the Ising model, which is the Monte Carlo algorithm.
A Monte Carlo algorithm is an algorithm often used in computational sciences. It allows to compute equilibrium properties of a system by making several different snapshots of the different states of the system.
Scientists have studied this phenomena thoroughly for a very long time. But there's a similar leap between seeing it on a computer screen and performing, acting it out yourself. The latter requires a greater involvement and a somewhat embodied understanding of the laws governing that phenomenon. Reducing complexity to the range humans are best suited to grasp is a powerful tool. I think it can also be the catalyst of a different kind of artistic expression in a radically interactive way.